Um, and I did you get a chance to work on some of these last night at all? A little bit? A little bit? Okay. Anna shaking her head. All right. Okay. All right. Uh, we've got a couple questions. I think we left off, and I think we're on question 16. Is that where we left off last time? 16? All right. Let me get my pen, and we'll talk about this. It says here, the central atom in which of these polyatomic ions cannot expand their octet. Okay. Now, first of all, expanding an octet, that means having more than 8 electrons around the central atom, and you can only use atoms in period 3, row 3, or lower. Okay, that's the key. So you look at this, and your first two, you've got the nitrite atom, or polyatomic ion, and you have nitrate. Nitrogen is in period 2, row 2. They can't expand their octet. The most they can have, 8 electrons. So it would be, the answer for that one would be 1 and 2. Okay. And then we're looking at number 17, the Lewis structure of which one cannot be drawn without a non-zero formal charge. Let's read that question again. Cannot be drawn without, in other words, which one's going to have a non-zero formal charge on it? So let's take a look at the possible Lewis structures for these and calculate the formal charge. I think it's a good exercise to make sure you can do that. So nitrite has 5 electrons plus 12 electrons, 2 from the oxygen plus 1 electron for the charge. So it's a grand total of 18 electrons. Okay, no big deal. Let's put our nitrogen in the center, our oxygen's on the outside, and then I've used 2, 4 electrons. I'll start on the outside. 2, 4, 6, 8, 10, 12, 14, 16, 18. Well, there's one possible structure for this, but it's not a good one because nitrogen does not have 8 electrons around it. So I can do this. 2, 4, 6, 8. So there you go. There's a good structure. Also has a resonance structure. By the way, that's a -1 charge. Also has a resonance structure. Now let's see if we can calculate the formal charge for the central atom here. Nitrogen has 5 electrons. I'm going to subtract 2 for the non-bonding electrons. And then 2, 4, 6 divided by 2 is 3, minus 3. So 5 minus 2 minus 3. That's a 0 formal charge on the central atom here. Okay, so that one is not going to be the answer. Let's look at nitrate. Nitrate. Okay, we've got 5 electrons, and we've got, see, each oxygen has 6. It's 18 electrons plus 1 electron. So that's going to be 24 electrons total. 24 electrons total. Put the nitrogen in the center. Boop. Put the oxygens like so. And I've used 2, 4, 6, so I have 18 to place. Well, if I do this, 2, 4, 6, 8, 10, 12, 14, 16, 18, that's not a good structure because nitrogen doesn't have 8 electrons around it. So you have that, or you also have resonance structures. You can have it like that, or you can have it like that. And I'm not going to fill in all the other electrons. So let's go ahead now and calculate the formal charge on the central atom. Normally has 5 valence electrons. No lone pairs, minus 0. 2, 4, 6, 8, minus 8 over 2, minus 4. That's going to be plus 1. Right? Plus 1. 5 minus 4 is plus 1. So there's your answer. That has to have a plus 1 formal charge on the central. That means one of these oxygens has to have, well, the formal charges have to add up to the negative charge. So if that's a +1, let's just take a look at the formal charges on all the other atoms here, just to see if they all add up to -1. Well, this oxygen normally has 6 valence electrons, -6, -1/2 of 2, so that's going to be 1. So this has a -1 formal charge, and this has a -1 formal charge. And so all the formal charges add up to -1, which is exactly what should happen in these Lewis structures. You can always check yourself on those if you're good at that. Okay. Number 19, Lewis structures of which ions can be drawn with all formal charges being 0. Well, I don't think I need to necessarily go in and do that problem. It's just the same thing here. You could draw each of the structures there and calculate the formal charges on the central atom. And if you have any problems with that, just let me know, and we can certainly go over it. Okay, 19. Oh, we just talked about how about the central atom in blank does not violate the octet rule? Well, if I go ahead and look at these, if I had a guess off the top of my head, I would say letter C for carbon tetrafluoride, because carbon cannot violate the octet rule. But let's take a look at some of these others to show that they do violate the octet rule. But that's a good thing. I mean, you see something in period 2, one of those atoms, nitrogen or not phosphorus, nitrogen or carbon or oxygen, they're not going to violate the octet rule. Okay. Everyone following along okay? I know it's not the most exciting stuff on the planet. Feel free to chime in if you want to. Let's take a look at KRF2. Very strange. Krypton difluoride. You don't see too many krypton compounds, as a matter of fact. You usually see more xenon compounds. I'm not even sure if this one really exists. I'd have to look it up because I've never seen krypton difluoride. But let's draw a Lewis structure for it. Even if it doesn't exist, we can come up with a Lewis structure for it. Krypton has 8 electrons, and fluorine is going to have 7, but I have 2 of them, so that's 14 electrons. So I've got, what, 22 electrons all day? Krypton in the center, fluorine on the ends, 2, 4, 6, 8, 10, 12, 14, 16. So then I've got 22, so I have 8 more electrons to place, right? No. How many have I used so far? 2, 4, 6, 8, 10, 12, 14, 16. Yeah. What's 22 minus 16? 6?
Yeah.
Right, 6. Gotta think. 1, 2, 3, 4, 5, 6. So you're going to have, in this atom, krypton, you're going to have 2, 4, 6, 8, 10 electrons around the central atom. If I were to look at this and try to determine the electronic geometry, it would be an AX2E3. So it would be a linear molecule shape-wise, but electron geometry would be trigonal bipyramid. And it'd be using dsp3 hybrid orbitals. So remember, those hybrid orbitals come into play for shapes. So, and you could prove to yourself that looking at all of these other ones, you're going to go ahead and violate the octet rule. And if you want to draw them out, you know, xenon tetrafluoride, you know that's going to violate it. SF4, let's take a look at SF4. Sulfur, we've got 6 electrons, and I've got 28 electrons for the 7, or the 4 rather, fluorines. So I'm going to end up with 32 electrons all total. So I'm going to have an S, my Fs, and 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26, 28, 30, 32. Wait a minute. What's that? Yes, 34. I can't count this morning. I'm tired. There you go. You got to put those on the central atom. They're not going to go on the fluorine. That cannot expand its octet. Now sulfur has 2, 4, 6, 8, 10 electrons around it, so it violates the octet rule. All right, good stuff. Skip the bond energy stuff. Number 23, as the number of covalent bonds between two atoms increases, the distance between the distance between the atoms what? Decreases. And if you had a guess about the strength of the bonds, which do you think would be the stronger bond? Single, double, or triple? What do you think is going to be the strongest to try to tear those bonds apart? The triple bond, yeah. Triple bond is a stronger bond to rip apart, followed by the double bond, and then followed by the single bond. Okay, so the answer with that would be decrease and then increase. So that'd be letter D. Number 24, according to VSEPR theory, if there are 3 electron domains in the valence shell of any atom, 3 electron domains, doesn't matter if they're bonding or not. So I'm going to have something like that or like that, and those things. In other words, we can call it an AX3 if we want to. And that would be what shape would that be? Trigonal planar, good. Bond angles, if you would draw it, would be actually about 120 degrees. Wonderful. Okay. According to VSEPR theory, if there are 5 electron domains in the valence shell, what will they be? Well, you'll look at your chart. Just call it AX5. What do you see for the shape on that? Trigonal bipyramid, yeah. It's going to have, your A in the center, and you're going to have, like, if this is the plane of the board, well, you're going to have an X there, an X there, and an X there. So these 3 are going to be in one plane, and if you were to draw it, it would look like a trigonal bipyramid. Okay. Interesting, because in this molecule we have 2 different sets of bond angles. We have the ones sort of popping up from that plane. Well, those bond angles will be 90 degrees. But these bond angles in the plane, they're going to be 120 degrees. So very, very interesting little geometry there. Okay, number 26. The electron domain geometry and the molecular geometry of iodine trichloride are blank and blank. Well, let's draw it and find out. ICl3, 7 times 4, 28 electrons. Got that number right. So I'm going to put I in the center. And I'm just drawing a Lewis structure here. We don't know what's going to be shape, so I'm just going to draw this Cl, Cl, Cl. And I do 2, 4, 6. I've got 22 electrons left to go. 2, 4, 6, 8, 10, 12, 14, 16, 18. So I've got 18, 20, 22, 24. So I'm going to have to put the rest of the electrons here. So if I look at this, I have got electron domain there, 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 and there, AX3E2. So that should correspond to a T shape for my molecular geometry, if you look at an AX3E2. But for a molecular geometry, it should be T-shaped. But for electron domain geometry, it should be trigonal bipyramid. And once again, guys, this is not something you have to memorize. You've got your little Rosetta Stone to guide you through. So if you think of it that way, if you can draw the Lewis structure, you're golden. Okay. Now, number 27. You don't have to overthink this. Let's take a look at this. Our choices for molecules are the following. one of the things you want to be able to do is, especially if you're looking at, what's wrong, Anna? Are you confused?
Oh, no.
Okay, good. Just if I'm going too quickly or something, just stop me. Again, I'm recording all this so you can watch it time and time again, or not at all if you don't want to. Smash that subscribe button and smash that like button. Give me some views so I can get monetized, get about 1.5 cents for my chemistry videos. Now, I look at this and I say, they're asking which of these is square planar. Now, as we talked about last night when we were looking at the SAT questions, you got to know sometimes some answers you can just get rid of right away. This is an example. So if you saw this as a multiple choice question, they're saying which one is square planar, and you have C, Cl4. Well, we should know that looking at this, it's very closely related to CH4. I mean, in terms of its bonding and its shape. And what shape was CH4 methane? That's one we should remember off the top of our head. What was that? Pretend there's another. Yeah. Oop, tearing apart Jack's stuff he buys online. Ignore that, please. So anyway, I have this little molecule here. What shape is that? Begins with a T and that ends with a hedron. Tetrahedron, good. Know that. Anything that is like that, with a carbon in the center and 4 bonds to it, is going to be tetrahedron. Cross that off your list. Bang. And then you have xenon tetrafluoride. Hey, that could be a contender. That could be a contender. And then the other one's ICl3. That can't be square planar because you got 3 things bonded to I. What you're not going to be able to do it. Xenon difluoride. No way that's square planar. It's not going to happen. You don't have 4 things bonded to the central thing. pH3, you should know that is going to look a lot. It's going to look exactly like NH3 because phosphorus is just 1 step down. So by process of elimination, that goes away, that goes away, that goes away, and that goes away. So you could prove to yourself that that's going to be square planar. As a matter of fact, it's an AX4E2. If you were to draw that, up, and then the fluorines, and you would look at your chart, you'd find out that's square planar. Good. All right. The molecular geometry of the hydronium ion. Well, let's see what we got here. We've got H3O with plus charge on it. So I've got 3 electrons from the hydrogen. I've got 6 electrons from the oxygen, but I'm going to take away 1 electron because it has a positive charge. So I've got 8 electrons to spread out over this molecule, or this polyatomic ion. So I've got my oxygen. Let's just do this. H, 2, 4, 6, 8. So this is going to be an AX3E. That's the positive charge on it. So what shape is AX3E? Trigonal pyramid. Yeah, see? This stuff isn't too bad. Now, carbon disulfide, right? Everybody in here should know what carbon dioxide looks like. Carbon dioxide, we've seen it quite a bit. You say, well, carbon disulfide. Sulfur is just one down from oxygen. C, S, S. It's a linear molecule. AX2. Okay. That's why, it's so important to know representative molecule shapes or polyatomic ion shapes. It'll help you. In that way, you don't have to waste time. You finish something up like this in 5 minutes. Okay, PF4 with a positive charge. Well, let's go through this one. Okay, so we've got 5 electrons from the phosphorus, and we've got 28 electrons from the 4 fluorines, and we're going to take away 1 of them because it's a positive 1 charge, so that's going to be 32 electrons. P in the center. Just going to stick my fluorines there. I've used 8 electrons so far. 8, 10, 12, 14, 16, 18, 20, 22, 24, 26, 28, 30, 32. So what shape? We have an AX4. What's that going to be? Tetrahedral. Yeah, so you guys are getting this. Beautiful. Okay. Now, this one may have caused you some problems because I didn't specifically address this particular one of these particular molecules. Let's talk about boron for a second. Boron is a strange breed of cat, like Joe Biden would say. Come on, man. Boron is in that netherworld between atoms that need an octet and atoms that are kind of tiny and maybe violate the octet rule. Boron is quite happy to only have 6 electrons around it. Okay. It's small. So if you ever see boron bonded to 3 things, it will adopt a trigonal planar arrangement, and the bond angles will be 120 degrees. But again, I didn't really address boron because it's one of those strange things like hydrogen can only have 2 electrons. Boron can violate the octet rule by being perfectly fine with 6 electrons. Just too small. So, there's that one. A lot of Lewis structures on this one and VSEPR structures. Well, let's keep chugging along then. I don't mind. How are we doing on time? Oh, we have 15 minutes yet. This is going to be a long video. All right. BrO3 with a -1 charge on it. Looks like a V. So I got 7 electrons from the bromine, plus 18, plus 1 electron. So 18 plus 8, I've got 26 electrons all totaled. Put my bromine in the center, my oxygens, and I've got 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26. And the whole thing has a negative charge on it. So I've got an AX3E. Look at your chart. What's the shape? Trigonal pyramid, yeah. A trig pier. Speaking of trig, how was it today? Good. Learn anything about sine and cosine? No. Ha! All right. You just let me know when you start talking about sine and cosine, then I will have a party. Yeah. Matter of fact, in 10 days we have to have a party. It's the old man's birthday. Yeah. Okay.
Magically begin to understand this.
You'll get it. It takes practice. This stuff is, I think this part is kind of fun over here. Let's take a look at this molecule. And as long as you remember certain things about the geometry around the carbons, you can get this right away, this stuff. Now it says, what is the geometry among the leftmost carbon? Well, you just block out the rest of the molecule. This is an AX4. It's going to be a tetrahedral. And it's going to be sp3 hybridized. Boom, done. You look at this carbon, it's an AX3. AX3, and this carbon right here is going to be sp2 hybridized, and the bond angles will be 120 degrees. So this part of it's going to be square planar. You can even play the game with the oxygen. This oxygen, AX2E2, it's going to be sp3 hybridized, and it's going to be bent. So you can look at any part of a molecule now, and with your techniques of VSEPR, boom, you can determine the geometry around any part of a molecule. Yes, Anna. I did far more than they were asking in that question. The answer is tetrahedral. But my point is, hey, if I put something like this on and it wasn't multiple choice, I would say determine, and this is exactly how I would phrase it, determine the molecular geometry around each of the atoms in this molecule, determine the molecular hybridization, and the approximate bond angle. I think that's a good, fair question. Yes?
So what's the difference between a tetrahedral and a square planar? Because they both have 4 around them.
A square planar, though, is AX4E2, right? So square planar means that, let's say I've got xenon tetrafluoride. All of these bonds, all of these are going to be in the same plane. This is a flat molecule. It has a 4-fold symmetry axis, which means that the bond angles are all 90 degrees. So if I have something that's square planar, I can turn it by 90 degrees. Let's say the fluorine's looking at Mackenzie. If I turn it by 90 degrees, the next fluorine's going to look at her 90 degrees, 90 degrees. So that's called an axis of symmetry. Whereas a tetrahedron, the tetrahedron, well, it doesn't have a 4-fold axis of symmetry. It's a 3-dimensional molecule. This is really interesting because it has a 2-fold axis of symmetry if you reflect through the molecule. So I'd have to spin it that way and then reflect the bottom to the top, and you'd have the same molecular geometry. We're going to spend some time, and this is something you'll never learn in high school, in any other high school in the country, about symmetry elements in molecules and how they relate to molecular polarity. It's kind of like my little gift to you. Probably rather a cake or something. So, let's keep moving. Keep on moving. Okay, now, in this molecule, this is exactly what I was talking about. Is that Mr. Eastman out there?
Yep.
Hey, come on in. We are doing our major review for their big test on molecular geometry.
Awesome.
Yeah, and molecular orbital theory. This doesn't have molecular orbital theory, so tomorrow I want to kind of wrap up with that little discussion on polarity. All right, so let's take a look. I'm going to draw this. I'm not going to tell you the answer, and we're going to go ahead and figure it out just like I told you before. So this is an amino acid, and you can tell because it has an amino group here. I'm sure that you learned this in Mr. Reichenbach's class. Probably talked about all the essential amino acids. Did you? Or am I just a long time ago?
I don't think we did.
You didn't talk about amino acids?
A little bit, but not much.
Oh, amino acids. These are the building blocks of proteins, right? And they come together doing condensation reactions and form very, very long chains. I don't know which one this is in particular. I don't really study biochemistry. I just recognize that this is an amino group and this is a carboxylic acid group. So let's analyze the geometry around each of the molecules. Okay, that part right there. What do you think it's going to be around that nitrogen? AX3E. Isolate them. AX3E. Trigonal pyramid, right? Good stuff. How about this guy right here, this carbon? Not trigonal pyramid. It's an AX3, right? Trigonal planar, yeah. I'm going to just call that, well, I can't call it TP because that's the same as trigonal pyramid. So we'll just call it trigonal planar. Trig plan. That's what you need. So 120-degree bond angle there, sp2 hybrids. Look at this carbon. AX4 shape, tetrahedral, good. This carbon, trigonal planar, sp2 hybridized, bond angle is 120 degrees. How about this oxygen? You're We're going to bent on that one. AX2E2. All right, good stuff. I think I can. I'm not going to comment on these polar molecules yet. Let me get to that tomorrow. Oh my lord, this just keeps going on and on and on, doesn't it?
Are we gonna have to know the angles, like the degrees?
It's on your sheet. Should be. I don't know. I don't think I necessarily have to go through these. I can make a supplementary video on this stuff because all it is drawing the Lewis structure, looking at your chart, determining the geometry, and looking at the hybrid orbitals. That's it. Let's just skip to number 48 and take a look at that. This is a good example of a problem. And I promise you there's going to be something like this, identifying sigma bonds and pi bonds. Okay, so drawing this guy right here, it's some sort of a carboxylic acid. An interesting one because it has a double bonded carbon in it. Got a methyl group down here. And I've got my carboxylic acid functionality here. That's the organic acid part of it. This is a carbon-carbon double bond. So this is what you call a functional group in organic chemistry. This is a functional group. They do things. You can do chemistry around those things. Hopefully by the end of the year we'll get a short unit on organic chemistry. I'd love to be able to get to that point. So let's take a look. What kind of bond is a single bond? Sigma. All right. So I got sigma, sigma, and then one's a what? And one's a what? Sigma and a pi, right? And sigma, 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 sigma pi, sigma, sigma. Done. If you have something like this, then this would be a sigma bond, a sigma, and then I'd have two pi bonds there in a triple bond. Okay. So last thing I want to talk about tomorrow is I want to review molecular orbital theory. You know, taking atomic orbitals, making molecular orbitals, and talk a little bit about bond polarity and how the symmetry of a molecule dictates its polarity. Whoa, 32 minutes. It's going to take a while to upload. Thank you very much.